So for example, my good friend Mr. Earl was not here yesterday. You're definitely going to want to go back and watch this video. But we can say that for problem number 21, everybody, whether you're here or not, you should be able to say, what x value can you not plug in for problem 21?
3.
How come?
Because you can't have 0 in the denominator.
Very good. So by the bottom, we say x cannot be 3. Okay, that's part of the domain. There's more to the domain than just that. We also want to look at the top. Can you take the square root of any number?
No.
No. What kind of numbers can't you take the square root of?
Negative
numbers. So therefore, the top, we say x plus 2 must be greater than or equal to 0. As we subtract 2, we get x is greater than or equal to -2. Now, these two statements contradict one another. So we want to express our answer in interval form. Look at this. X greater than -2? Well, 3 is greater than -2, yet it can't be 3 either. So to make sense of this, I'm just going to draw a small little graph. I'm going to put the numbers -2 and 3 on it. I include the number -2, arrow that way, but I want to exclude the number 3. So this is our true domain, and we are going to represent this in interval notation as -2 to 3 union 3 to infinity. Keaton, give me a number to the left of -2.
-3.
So he picks the number -3. So that means that -3 should not work out if I plug it in because it's not included. Watch what happens. On the bottom, I get a -6. On the top, I get a square root of -1. And what is the square root of -1? I. You get imaginary numbers. So therefore, we can see that -3 is not a number that works. Jacob, give me a number to the right of -2. He gives me -1. If I plug in -1, I get the square root of 1, which is 1, over -4. Is -1/4 a number that you can plot? Absolutely. So that means that -1 is part of the domain. So you can always go back and plug in some numbers and check to see if your interval notation matches the appropriate domain. Try the next one on your own. Don't expect to get the whole thing right, but do your best. See if you can state the domain. Okay, let's see what you're coming up with. On the bottom, you see a cubed root. Can you take the cubed root of any number?
No.
You can. Watch. The cubed root of 8 is 2. The cubed root of -8 is -2. The cubed root of 0 is 0. You could take the cubed root of positives. You could take the cubed root of negatives. You could take the cubed root of 0. Take the cubed root of all sorts of things. However, it's in the denominator. What number are you not allowed to divide by?
0.
And so what number would give you 0 in the denominator?
2.
So therefore, x cannot be 2. So the cubed root part is fine, but the fact that you could get 2 or 0 in the denominator, that makes it not okay. The top part, we see the square root of x plus 4, and we know that x plus 4 must be greater than or equal to 0 because you can't take the square root of a negative. So x is greater than or equal to -4. Well, those contradict one another. And if you plot -4 and draw your arrow off to the right, and you plot +2 and exclude that, it turns out that our possible domain is from -4 to +2, union positive 2 to infinity. Okay? I would say that those problems would be on the slightly more challenging side. Okay? So what we're going to do right now is stuff that you did not have to be here for yesterday. So please flip on over to this part where it says 2.2 graphs of functions. The first couple things that we're going to do are going to be pretty easy. The last thing we're going to do is going to be a little bit more challenging. Okay? And if you can make it through this next challenging part that we have at the end, you're really set to get a good grade on this next test. We want to remind ourselves graphically what function notation means. You can plug in -2 to a function and get an output. You've already done that. But graphically, it means if you have an x value of -2, what is the height of the function at that spot? It is 1. I have f of -1. Notice I have an open circle and I have a closed circle. Do you think I'd choose the open circle or the closed circle when I'm evaluating the function? I choose the closed one, and notice it also has a height of 1. Now I'm going to do f of 0. I go over to 0 and I see what the height of the function is at 0, and it is 1. And then I go over to f of 1. I notice I have an open circle here. I have an open circle there. I have a closed circle down here. Which one do you think I grab?
-2.
The closed one has a height of -2. And then finally, f of 2, again, has a height of 1. So you should be able to look at a graph and generate outputs by looking at the height of the function. A review from the other day, we should be able to state the domain and the range of the function. In order to state the domain, what I like to do is I like to grab that vertical line and I like to drag it across. We'll say that this graph does in fact have arrows on the end of it for the sake of this problem. Will this graph eventually cross my vertical line?
Yep.
How about now?
Yep.
Now?
Yep.
Now?
Yep.
Yep. Here?
Yeah.
Yep. How about here?
Yep. 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 Yep.
So the domain is going to be from -infinity to positive infinity. No matter where you put this line, it has a function value at that spot. So the domain is from -infinity to positive infinity. In order to determine the range, we don't grab the vertical line, we grab the horizontal line and we drag that up and down. I would like you right now to try to see if you can identify what the range is of that function. Try the range on your own. I have my range starting down at -infinity, and it continues on up. I have values here. I have values also here. But I start to run out of values when I get to the value of 2. So it goes to 2. Notice how I have a parenthesis and not a bracket. Okay. Any questions on domain or range? The third question, the domain values that satisfy f of x equals 0. This is your x value, this is your y value. So the question is, if I look at my function and I look at when does it have a height of 0, I want to know the corresponding x values. So you tell me when I get to a height of 0 on the function.
There. -3.
Yeah, right there. And then we would say there, but it jumps up here now.
There.
Yep. So at x equals -3, that produces an output of 0, and x equals 4 produces an output of 0. Yes?
So since the circle is open on -1, that's not a value.
Exactly. If it would have been closed circle here and open circle there, then we would have included -1 as well. Good question. Flip it over. These do not have to be exact by any stretch of the imagination. Go ahead and draw. Whoop, that was a really bad example. Try that again. Go ahead and draw those 4 shapes. It can be very general. One thing we'd like to remind you of when it comes to functions is that in order for a function to be a function, it must pass what we refer to as the vertical line test. And the vertical line test is very simple. It just states that if you take a vertical line and drag it across the graph, it can only touch the graph once, wherever you place it. So if I place it here, it touches once. If I place it here, it touches once. And notice anywhere I place it, it only touches the graph once. So therefore, yes, this is a function. Is the second one a function?
No.
No. Is the third one a function?
No.
No, because when you put it here, it overlaps that vertical line, so it crosses an infinite number of times. How about the last one?
Yes.
Yeah. So the first one is a function, the second one is not. The third one is not, and the fourth one is. You should also be able to determine if something is a function by simply looking at the equation. We'll see how you guys do with this. Didn't get much of a response first hour. Hopefully you guys see something a little bit more there. I think that they were still waking up. I subtracted 2x squared from both sides. I get a negative 4y is equal to negative 2x squared plus 8. And I divide by negative 4. And I get y is equal to 1/2 x squared minus 2. Now, the reason why I did that is I'm trying to solve for y to see if I give an input, how many outputs I get. Araya, give me a number, any number. 3. She plugs in 3 and she squares 3 and she gets 9. She multiplies by 1/2 and she gets 4.5 minus 2 is 2.5. Do you agree that if you plug in 3, there's only one number that you're getting out?
Yeah.
So therefore it's a function. She's only getting out one result. The next one, if I were to solve for y, I subtract x squared from both sides. I get y squared is equal to 9 minus x squared. In order to solve for y, I must take the square root of both sides. And notice when I take the square root of y squared, if I take the square root of a y squared, I have to produce how many solutions? If it's y squared, I'll have 2 solutions. So I have a positive and a negative y is equal to the square root of 9 minus x squared. Now, before Araya gave us 3, I'm going to choose a number now and show you how this is not a function. If I plug in the number 0, 0 squared is 0, and 9 minus 0 is 9. The square root of 9 produces 3, right? But this says I got to list both positive 3 and negative 3. So therefore, if I plug in 0, I have 2 outputs. That is not a function. Now, we'll see if people know this. Please, it'll make me so proud. You already knew this wasn't a function because what does that graph look like?
Circle.
It's a circle. Thank you. Give it up for Legend. You know it's a circle because we did that last unit, right? Exactly. X squared plus y squared, the center is at 0, 0, and the radius is 3. So you knew it wasn't a function right away. You knew that this was a function because it makes a parabola. When you can connect the algebra with the graph, that's an important step. Okay, good job. We don't need to do the last one. We end with example 4 right here. Okay, this is where it gets just a little bit messy. As I start to write it down, I'm going to tell you guys, please do not make a permanent kind of notes right now, because I'm going to erase what I'm writing down in just a second. I have piecewise functions. You remember before that we said if you're doing f of 3, do you plug it into the top or the bottom? Do you remember?
You plug it into the bottom.
The bottom, because 3 is greater than or equal to 2. Remember that?
Yeah.
Now we don't want to plug values in. We actually want to sketch a graph and see what this piecewise function looks like. Okay? And so here's what we're going to do. We're going to look at each of these functions. The top one is y is equal to 3, and the bottom one is y is equal to x minus 4. And we're just going to try to get in our brain what each of those functions looks like. Does anybody remember what y equals 3 looks like? What kind of shape is that?
Isn't it just a line?
It's a line that happens to be horizontal through 3. So I'm going to sketch that. You don't have to, because if you do, you're going to have to erase part of it, okay? I sketch that, and then I have y equals x minus 4. That's a line as well, but the slope is? Slope is 1, and it passes on the y-axis through? -4, so I know that one as well. It's right here, okay? So if I drew both of those down, I can see that that doesn't pass the vertical line test. It crosses twice, doesn't it? It turns out I don't want the entire function. I only want a certain portion of it. For example, I only want the graph of 3 up until the x value of 2. So I only want that portion of the graph. I don't want the rest of it. And then this one, I want from the value of 2 all the way on after that. The blue is what I actually want. I don't want the remaining red. You see that? Now, I do have a student in one of my classes right now that when they sketch their piecewise function, they do that. They do a light graph, and then they do a dark graph over that they actually want. That's not the way I teach it, but you sure can do that. That's absolutely fine. I'll show you how I teach people how to sketch the graph. The first thing I do is I just try to tell people to keep those in mind, and then I work on finding the endpoints. There's an endpoint at x is equal to 2. And if I plug 2 into this function, it says the output is always 3. So I'm going to draw the graph of 3 all the way up until I get to the coordinate 2, 3. I put an open circle because it just says less than. It doesn't say equal to at all. Then I move down here. I plug in 2, and I see that the output is -2. So that means my endpoint for this graph is going to be 2, -2. I have a closed circle as it says equals, and then I draw the graph with a slope of 1 the rest of the way. So I like to come up with the general idea of the graph, then figure out my endpoints, and then draw. Okay? Araya's doing the kind of the furrowed brow right here. Okay? She's thinking about it critically. That's really good because people make mistakes with these. We want to be able to take time and figure them out. Now, here's what I want you to do. I want you to just very, very lightly make a sketch of what that looks like and make a sketch of what that looks like. Very light. Either off to the side or on the graph, and see if you can come up with what do those look like. That's the first task in your mind, okay? Go ahead, take 30 seconds, come up with a quick sketch of what each of those look like. Okay, 5, 4, 3, 2, 1. When you see x plus 3, I want you to be able to right away think of something that looks like that. And when you see x squared, I want you right away to think of something that looks like that. Everybody on the same page? Got that locked in? Okay, hold that in your brain. And so now that we have that in our brain, what we're going to do is we're going to figure out the endpoints. And to figure out the endpoints, I'm going to go ahead and plug in a value of -1. And if I plug in a value of -1, I get an output of 2, because -1 plus 3 is 2. Open or close circle? Close circle at -1, positive 2. And now I'm going to draw the graph with a slope of 1. Some people don't like that because they say you drew it going down. No, folks, from left to right, it's going up. Slope is from left to right, not right to left. So from left to right, it's going up. So it's a +1 for your slope. Some people say, well, you didn't go through 3. Well, I can't go through 3. I have to stop at x is -1, so it doesn't quite make it. If it was, x less than or equal to 2, then sure, I could continue to draw through 3, but it's less than -1, so I can't do that. Go ahead and plug -1 in the bottom, and when you plug -1 in the bottom, you get 1. So I have an open circle at negative 1, 0. And I remember that this shape made a parabola that went down to 0 and came back up. And so that's the graph that I want. That's the piecewise function. As we finish this off, take the last one and see if you can lightly sketch those 3 graphs. You got 3 of them. Lightly sketch those 3 graphs. Okay, glance up here. 4 minus x squared should be upside down and shifted up 4 units. The graph of negative 2 is a horizontal line through negative 2, and x minus 5 should be a line with a slope of 1 going through negative 5. Are we all good with those 3 graphs? Okay, then let's figure out the pieces of the graph that we want to actually produce. We plug in 1. What do I get when I plug in 1? 4 minus 1 squared is 3. So I plot 1, 3 with an open circle. And remember the graph of 4 minus x squared. That is a graph that went up to 4, came back down. We're just showing that portion of the graph. Then I have the graph of negative 2. It looks like I have 2 endpoints. And when you plug in 1, you get negative 2. And when we plug in 3, we get negative 2. Notice that both are open circles. And we remember that the graph of 2, negative 2 is just a horizontal line, just like I've shown there. And finally, for the last one, we plug in 3, and it also produces negative 2. This still tells me it remains an open circle. So I plot 3, negative 2, which is already right here, and then I head on up with a slope of 1. And that's the piecewise function. Grab your homework. So we can just talk about where you're at right now, what you're doing. Yesterday we were looking at domain and range graphically, just like this, okay? And then we also were talking about the domain by looking at the equations from an analytical point of view, okay? After that, you move on today to the graphs of functions. And the first page should be pretty simple, and even the second half should be pretty simple until you get to the bottom. There are 6 piecewise functions that you want to do. Sometimes people get through the first part, and they say to themselves, hey, this ain't bad. And they get to the piecewise functions, and they don't know what they're doing, and they wait till like the night before the test to try to figure it out, and they never do. And it's the day of the test, and they come and they say, Mr. Gaines, I don't want to do it on piecewise functions. It's like, well, that's a tough deal. So we want to figure that out sooner than later. Please make sure that you come tomorrow ready to ask questions about domain as well as your piecewise functions. We are beyond the point of dumb questions. Okay, there are no dumb questions. So if you're struggling with piecewise functions, chances probably a third of the class is too. So don't be afraid to ask that. So we'll have time tomorrow to work. The rest of the time is yours right now. I'm going to upload a video from yesterday.